Hello everyone, welcome to Unacademy, India's largest online learning platform, which is helping the students of all walks of life from all parts of the country to realize their dreams. Okay, today we will be discussing about lecture number 9 of electronic devices and circuits of semiconductor physics. Just a second, I'm just looking whether am I visible to all of you or not. Number 9 of electronic devices and circuits of semiconductor physics. Just a second, I'm just looking whether. Okay, sorry. So it's going to be EDC Semiconductor Physics, section number 9. So myself, Shravan Kumar, I have a master's degree from JNTUH in VLSI System Design. I have 10 plus years of teaching experience, and I can handle the subjects like EDC, analog electronics, digital electronics, and EMFT. And then I have a special code for you guys, that is SVS10, which will give you 10% discount on Unacademy. Which will give you 10% discount on Unacademy plus subscription. Unacademy plus subscription. Okay. So what do you mean plus subscription? Plus subscription will give you access to the live classes. You can attend all the crash courses. You can attend all the weekly tests. So these weekly tests are very, very important. These weekly tests are very, very important. And you will be having a doubt solving session. Every 4th hour is going to be a doubt solving session. And then you will be having sessions in English and Hindi. That is, those who don't understand English, they can attend all sessions in Hindi. Right? We have something called rank improvement batch. So this will help you to improve your rank. But we have something called iconic subscription. Along with the benefits of plus subscription, you will be having extra benefits like personal coach. You will be given a study planner, a study book sessions, a personal test analysis, and a preparatory study material will be available for all you guys. Okay. Then plus subscription for 12 months is 27,225 rupees. Plus subscription for 18 months is going to be 34,650 rupees. 650 rupees. Plus subscription for 24 months is going to be 39,600 rupees after using the code SVS10. Okay. So plus subscription for iconic subscription for 12 months is going to be 45,225 rupees. Iconic subscription for 24 months is going to be 66,600 rupees after using the code SVS10, which will give you 10% discount on it. Okay. And how to do it, sir? Simply download Unacademy app, install it, and then select your goal as the GATE ESE. Click on plus subscription, then click on get subscription, and you will be asked to select how many months. So simply select number of months and type SVS10 to get 10% discount and click on apply, and then the final price will be displayed here. Then click on proceed payment, and you will be having different types of payment methods like debit card payment, EMI, UPI, wallets, and net banking. You have all these types of payments methods, so you can use any one of the payment method. Okay. Yes, we'll be having Unacademy's biggest free scholarship test, sir, for GATE and ESE exams. So which is going to be conducted on 28th of this February. That is the coming Sunday. At 11 a.m. At 11 a.m. It has to be. We will be having the session at 11 a.m. So you should use the code SVS10. You should use the code SVS10 to enroll yourself. You should use the code SVS10. Okay. So then you can see this will be going to happen on 28th of February, as I told you. Just a second, I'm feeling a bit uncomfortable. Okay. So this will be for the ECE and triple and ECE students, and this will be for 60 minutes, and you should use the code SVS10. and first 3 students will be getting, winners will be getting 100% scholarship on plus subscription. You can see there the terms and conditions. And first 1 to 3 ranks will get 100% subscription. For 4 to 10, 75%, and 11 to 50, 50%. 51 to 100 will get 25% off on Unacademy Plus subscription. And a new batch of our Evolve 2022 fifth batch is going to start on March 5th, March 1st of the March. So use this code SVS10 to get 10% discount. Use this code SVS10 to get 10% discount. And then Evolve for ECE also will be starting on 1st of the March itself. So use the code SVS10. Use the code SVS10 to get that. To get that also. Assigned also another batch which will be starting for targeting GATE 2023. Again, this is also starts on 1st of the March. So SVS10 is going to be the code. SVS10 is going to be the code. And then Assigned 2023, GATE 2023 for ECE students, which will start on March at the 1st of the March. And you can use the code SVS10. You can use the code SVS10. Okay? Yeah. So before we discuss about what we discussed today's topic, let's go back and see what we have discussed in the previous class. In the previous class, we have discussed about mobility of charge carriers mu. Mobility of charge carriers mu. That mu is the charge mobility of charge carriers, which is the units of mu is going to be meter square per volt second. And then we have discussed about current density. Very importantly, we have discussed this current density. The units of the current density. So very simple. Current density, as I told you, density is nothing but generally we'll write population density. Population density is nothing but the number of people living by unit area. Generally we'll write number of people living by unit area. So generally current I by A we generally will write. So I current by area. So amperes per meter square is the unit. Amperes per meter square is the unit. And then we have seen the formulas. J is equal to J is equal to NQV, where N is electron concentration, Q is the charge of an electron, and V is the drift velocity. Remember, V is the drift velocity. V is the drift velocity. Then we have seen conductivity. So conductivity is going to be sigma is going to be NQ mu, where it was NQV. NQV for NQV is a current density, and sigma is going to be NQ mu is going to be the conductivity. Okay. And we have discussed the problems. Problem number 1 in detail we have discussed, and then I think we have discussed problem number 2 also. This problem also we have discussed in detail. And we started our discussion of bonding forces. Now again I will come back to that. So there are 2 types of bondings. So one is called ionic bond. And second one is called covalent bond. Ionic bond and covalent bond are the 2 bonds which are important bonds in any solid system. So it forms between the 2 oppositely charged ions, which produces by the transfer of electrons from one atom to the other atom. So in ionic bond, a transfer of electrons will happen. Transfer of electron will happen, right? So what do you mean by transfer of electron? Let's consider Na and Na, sodium, NaCl. Let's consider. So NaCl, how it forms, sir? How NaCl has formed, sir? NaCl has formed by donating. Na donates 1 electron, it becomes Na plus, and then Cl minus. Na plus and Cl minus. Right? So what is Na? What is Na, sir? What is the atomic number of sodium, sir? Atomic number of sodium is going to be Na is going to be 11. So how will you write, sir? You can write it as 1s2, 2s2, 2p6, 3s1. 1s2, 2s2, 2p6, 3s1. Right? Then what is chlorine, sir? What is chlorine? Chlorine is going to be 17. So how will you write, sir? You will write electronic configuration to be 1s2, 2s2, 2p6, 3s2, then 3p5. Right? So by giving this one electron, this will become, Na will become Na plus. Na becomes Na plus, and then accepting one electron, and this will become Cl minus. Cl minus. These two are ions. This is going to be positive ion. This is going to be positive ion. And this is going to be negative ion. This is going to be a negative ion. This is going to be a negative ion. Positive ion and going to be negative ion. One is going to be positive ion, the other one is going to be negative ion. See, now I'll tell you here why Na is Na plus, what Na plus represents. What Na plus represents. So now, so generally what is Na, sir? Just now I have told you Na is going to be 11. Na is going to be 11. So in case of Na, so we know that at the nucleus will be having 13 positive ions, around which 13 electrons will be revolving, right? So you will be having 13 electrons, 13 electrons which will be revolving around the nucleus, which will be around the nucleus, and the nucleus contains 13 protons, which is nothing but a positive charge. Nothing but a positive charge. Now what's happening, sir? One electron has gone out. One electron is donated. One electron is donated. When one electron is donated, now how many remaining? 12 electrons remaining is going to be remaining 12 electrons, and then 13 protons will be there. 13 protons will be there. That is, this is a negative charge. This is going to be positive charge. You can see here. If you look at here, this new Na. So which is very higher, sir? Is the positive charge is higher or negative charge is higher? Is the positive charge higher or negative charge is higher? Is the positive charge higher or negative charge? So this here. So one proton is more. One proton is more, which is of positive charge. So because of that, so plus 1 plus charge is extra. 1 plus charge is extra here. 1 plus charge is extra here. 1 plus charge is extra here. So that is the reason why this Na becomes Na plus. So that is how sodium has become Na plus. Similarly, chlorine. If you look at the chlorine, for the chlorine, we will be having 17. So here, at the nucleus, we will be having 17 positive charges, and you will be having 17 electrons. One extra electron is added. One electron is added here. One electron is added here. So how much it will become, sir? Now you will be having 18 electrons and then 17 protons. That is negative, and this is going to be positive. So which is extra now, sir? So one negative charge is extra. One negative charge is extra here. That is the reason why Cl has become Cl minus. That Cl has become Cl minus. So this is how a sodium becomes Na plus and the chlorine becomes a Cl minus. So the atom which donates an electron is called as a donor. And the atom which accepts the electron is called as an acceptor. So the atom which donates the electron is called as donor, and which accepts an electron is called as acceptor. So Na is donor and Cl is acceptor. Okay, because it accepts. So acceptor always becomes a negative and donor always becomes positive. Donor becomes positive and acceptor becomes negative. Okay. Then we'll be having something called covalent bond. So as I told you yesterday also, this is going to be covalent bond. Covalent bond. Covalent bond. The bond which is happening, which exists between the bond which exists between the valency, the bond which exists between the valence. Just a second. Okay, no issue. Sorry. So the bond which exists because of the cooperation or sharing of electrons between the neighboring atoms. So let us consider a germanium or silicon atom, whichever you want. Let's consider germanium atom. Let's consider germanium atom. So which will be having 4 electrons in the outer shell. 4 electrons in the outer shell. Similarly, you consider another germanium atom which is having 4 electrons in the outer shell, obviously, right? Now, here exists a bond between these two. So now what's happening, sir? This is sharing, this again, this also shares one electron here. 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 So this also shares one electron here. This also shares one electron here, like this. See what is happening here, sir? A germanium atom is this bond is called covalent bond. This bond is called covalent bond. Covalent bond. The bond which is existing because of the valency electrons, sharing of valence electrons. Sharing of valence electrons is nothing but covalent bond. Sharing of valence electrons is nothing but covalent bond. Okay, so this is called covalent bond. Okay, is that clear, sir? Is that clear? Okay, then this is sharing. Sharing of electrons will happen here. Because of that, it is called covalent bond. Because of that, it is called covalent bond. This is called covalent bond. Okay. Next, here comes the story of electrons and holes. So, which is very, very important, sir. So, at very low temperature, no carriers of electricity are available, and crystal behaves as an insulator. Remember one thing: at at, at 0 degrees Kelvin, 0 degrees Kelvin, there is no carriers of electricity. No free carriers. No free carriers. No free carriers. No free carriers. No free carriers of electricity. 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 Okay. No free carriers of electricity. And so because of that, now semiconductor behaves like an insulator. So semiconductor behaves like a a behaves like a insulator. And energy gap at this point. So the energy gap at 0 degrees Kelvin is going to be, energy gap is also very high. Energy gap is high. Energy gap is high at this point. Okay. Now as the temperature increases, As temperature increases. Now tell me what happens, sir. As temperature increases, the covalent bonds, just now what we discussed, sir, the electrons in the covalent bond, the electrons in the covalent bond, the electrons in the covalent bond gain some energy, get some energy, and they'll go out of the, they'll go out of the covalent bond, right? So this covalent bond will be broken. So as the temperature increases, covalent bonds will break. Some covalent bonds, some covalent bonds, some covalent bonds will be broken. 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 And then what happens, sir? Slowly they'll start conduction. Now, free electrons and holes will come. Free electrons and holes will come, and they'll what happens, sir? They'll contribute for the conduction. They'll start contribution. They'll start conduction. Right now, in the last class, how what I told you. Now you can see here. The beautifully I'll explain here. This is very important. Consider the germanium. So as I told you, you'll be having 4 electrons here in the outer shell. Similarly, let's say another electron is here, another germanium is here, so which is also having 4 electrons here. Harika, good evening. Good evening, Harika. So here you will be having a covalent bond. This is also a covalent bond. This is also covalent bond you will be having. This is also you will be having covalent bond. This also you will be having covalent bond. This is going to go into covalent bond. This is a covalent bond. Now, as I told you, as the temperature increases, some covalent bonds will be broken. Some covalent bonds will be broken. It means this electron will go out and come out for conduction. So when electron is coming out, when the electron is coming out of the covalent bond, it creates a hole here. 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 So as I told you yesterday, the absence of electrons in the covalent bond, the absence of electron in the covalent bond. Now, if you want me to represent, I'll represent with this green. So I'll do one thing. Here I'll do it as a green, so that you will at least find a difference, right? So the circle, it will be represented with the circle. The absence of electron in the covalent bond. The absence of electron. I'll write here. The absence of an electron. The absence of an electron. The absence of an electron. Of an electron in the covalent bond. In the covalent bond is called hole. It will be represented by a circle. Right? Now, what will happen with this hole, sir? Why we are so worried about this hole? This hole also contributes for the conduction. The important thing to be remembered here, the hole contributes for the conduction. The hole contributes for the conduction. Right? So it can also be useful for the conduction of the electricity. So this hole contributes, this hole contributes for the conduction. Contributes for the conduction. How it contributes? Let's understand how it comes, sir. Contributes for the conduction. Contributes for the conduction. Let's try to understand what does it mean. Let's try to understand what does it mean. Let's try to understand what does it mean. Let's say now what I'll do, sir. I'll have, let's consider a few electrons here and some holes like this. So let us say, we have electrons here. So these are electrons. Let's say these are electrons. This is electron. This is electrons. Let's say this is not the electron. That is a hole. That is a hole. Right? That is a hole. Right? Now what I'm trying to do here? Now listen to me carefully. let's say the electron, let's say this is going to be 1, 2, sorry, 3, 4, 5, 6, 7, 8. Let's say the electron in the fifth, sorry, the hole in the fifth, the electron in the fourth may try to go into the fifth place. Whenever the electron is moving from fourth place to fifth place, now what happens, sir? You can find here an empty space, in the fourth, but the fifth space is filled. The fifth space is filled, right? So you can see here, a hole is shifted from here to here. A hole is shifted from here to here, right? So actually, what is shifting, sir? Frankly speaking, I can say electron is moving in this direction. So electron moved from 4 to 5. But whereas how it is looking, sir? Hole moved from 5 to 4. 5 to 4. So if electron is flowing in this direction, electron flows in this direction, then the hole moves in the opposite direction. Hole moves in the opposite direction. Remember this point. So when electron moving from left to right, holes move from right to left. Or if electron is moving from right to left, holes move from opposite direction. So the flow of electrons and holes will be in opposite direction. So the hole moves always in the direction opposite to the electron. Remember, the flow of holes will be exactly opposite in the electron direction. The direction of flow of holes is exactly opposite to the flow of electrons. This is the very important point to be remembered. This is a very important point you should remember. Okay. Shall we go to next topic? Yeah, we go to next topic. Yeah, we have come something called here to discuss about intrinsic semiconductor. So what do you mean by intrinsic semiconductor? A perfect semiconductor with no impurities is called an intrinsic semiconductor. A perfect semiconductor. It is a pure, actually I should use a word pure or perfect. A pure or perfect semiconductor. A pure or perfect semiconductor with no impurity, without impurities is called an intrinsic semiconductor. It's called an intrinsic semiconductor. In an intrinsic semiconductor, the whole concentration must be equal to the electron concentration. This second point is very important. For an intrinsic concentration, for intrinsic semiconductor, the whole concentration N must be equal to P. Remember this point, very, very important. For intrinsic concentration, N must be equal to P, and that must be equal to, we call it as a Ni, where Ni is intrinsic concentration. We call it as a intrinsic concentration. We call this as a intrinsic concentration. Okay. So we call it as an intrinsic concentration. N is equal to P is equal to Ni. N is equal to P is equal to Ni. And where N is equal to intrinsic concentration. Okay. It means, how will see, what do you mean by this? Let me explain here. So, otherwise you don't understand. I'll just try to explain you what do you mean by this. So, what do you mean by this? I am a bit suffering with the cold. Please don't think like this. I have some issue with my health. I mean to say, from last couple of days, I am not feeling comfortable? So if this is the valency band, this is the valency band, this is valency band, this is conduction band, this is conduction band, this is conduction band. If you look at here, this represents number of electrons, number of free electron conduction band. I can write conduction band. So if you look at here, you can see how many number of electrons are. You have 4 free electrons here. So similarly, there will be 4 free holes, right? So these are called holes. These are called holes, and these are free electrons. These are called free electrons. Free electrons. Remember, always only free electrons will be responsible for the conduction. Only free electrons will be responsible for the conduction. So here, what is Ni, sir? So N is equal to 4. Then P is equal to P represents holes, sir. So N represents electrons. So Ni must be equal to 4. You should remember this. Ni must be equal to 4. That is, intrinsic concentration must be equal to 4. Intrinsic concentration must be equal to 4. So this is a very important point to be remembered. Always for intrinsic concentration, N is equal to P is equal to Ni. N is equal to P is equal to Ni, which is very, very important, right? So this you should remember. For intrinsic concentration, N is equal to P is equal to Ni. Okay, next. Next, here comes the story of something called extrinsic semiconductor. So what do you mean by extrinsic concentration, extrinsic semiconductor? Extrinsic semiconductor is nothing but as a impure semiconductor, is nothing but, so which is having so what impure semiconductor. This is again, as I told you, which is which is what we are trying to do, sir. Now we are trying to add, right? The process of adding external impurities, the process of adding external impurities, the process of adding external impurities to a pure form of semiconductor, to a pure form of semiconductor, is called doping. Okay, the process of adding external impurities to a pure form of semiconductors. So what do you mean by impurities? Impurities means it will be either pentavalent or trivalent atoms. Adding pentavalent or trivalent atoms to a existing pure form of semiconductor, which will make that semiconductor into impure, is nothing but doping. Sir, why we are doing this? Why we are doing this, sir? Why we are doing this? What is the reason behind it? Why we have to do? It is to create additional. So why we are doing, sir? To create additional, to create to create additional to create additional carriers. So the why we are creating this, adding, sir? So we are trying to create additional. We are trying to create additional carriers to increase conductivity, to increase conductivity, to increase conductivity. Okay, to increase conductivity, we'll be adding external impurities called either pentavalent or trivalent impurities, either pentavalent or trivalent impurities. So just a second. So here comes now just 2-3 points which I have to mention here. So which are very important for N type and P type. That is why I am trying to draw this. This is extrinsic semiconductor, extrinsic semiconductor, extrinsic semiconductor. Here you will be having N type, and then this is called P type. N type and P type. So here N type means, remember, electrons are the majority charge carriers. Electrons are the majority charge carriers in N type. In P type, holes are the majority charge carriers. Holes are the majority charge carriers. So it means, how will you get, sir, this N type? By adding a pentavalent atom. By adding a pentavalent atom. Pentavalent impurities you can write. So if you add a pentavalent impurities, this extrinsic semiconductor will be formed, which is called as a N-type semiconductor. So which group elements will help you this, sir? Which group elements will make this a pure form of semiconductor in extrinsic semiconductor of type N-type, sir? So if you add a fifth group elements will help you. Fifth group elements. Can somebody tell me what are fifth group elements? What are fifth group elements which you know? What are fifth group elements? What are fifth group elements, sir? Okay, I'll tell you, no problem. We'll be having phosphorus, arsenic, antimony, bismuth, like this you will be having. Right? So then what do you mean by P type? So P type will be, how will you create P type, sir? P type will be created by adding trivalent impurities. Will be added by using trivalent impurities. So if you add trivalent impurities, you will get this. So which group elements will help you, sir? The third group elements will help you. Third group elements will help you. So what are third group elements, sir? What are third group elements? Can somebody tell me? Boron, aluminium, gallium, and indium. These are the third group elements, but most of the time arsenic and then gallium are the most used trivalent and pentavalent impurities. Trivalent and pentavalent. Of course, phosphorus will also be used. Aluminium, sometimes aluminium also used, and boron is very rarely used. So phosphorus, arsenic, aluminium, and gallium are the indium. So these are the different extrinsic semiconductor materials which will be formed. Now we'll discuss in detail about what is N-type semiconductor. What is an N-type semiconductor? Now consider this diagram. So let us discuss about N-type semiconductor. Now we'll discuss about N-type semiconductor. So what do you mean by N-type semiconductor, sir? As I told you, yes, you are right, Mr. Vijay. Yes, you are right, Mr. Vijay. You are right. You can use the boron, aluminium, gallium, and indium. You are right. You are right. And entire semiconductor material is very, very important semiconductor material. So, which will be useful very much. Sir, if you understand this semiconductor concepts, then only you can go forward and understand the next topics of PN junction diode. After that, the BJT. After that, a MOSFET or MOS capacitor, whatever. So, this foundation is very, very important. Foundation is very, very important. Remember, an N-type semiconductor will be having something called a dopant. A dopant will have a trivalent impurities. Will be having a pentavalent impurities, right? Will be having 5 valency electrons. So we will be having 5 valency electrons. 5 valency electrons. Right? You will be having a 5 valency electrons. So whichever 5 valency electrons will be added to a pure form of semiconductor. Now you can consider, see here germanium is there. Here you can see the germanium is there. So germanium is having 4 electrons here, which is having another 4 electrons. Let's say 5 electrons, new 5 electrons is added. Let's say so pentavalent, consider some pentavalent, sir. Let's consider an arsenic. Let's say an arsenic atom is added here. If the arsenic atom is added here, assume that the arsenic is added here. So the 4 electrons of germanium will be shared with the 4 electrons, and you can see an extra electron will be appearing here. An extra electron will be appearing here. Just see, sir. See, just see what's happening here. This extra electron has come. Which is called a free electron. We call this as a free electron. And this free electron is responsible for the conduction. This free electron will be responsible for the conduction. So 4 of 5 valence electrons will occupy the covalent bonds, right? The arsenic, as I told you, arsenic has 5 valency electrons. Out of 5 valency electrons, so 4 of them will be occupied with the covalent bonds. 1 electron will be left free. That will help for the conduction. This is very, very important, right? Right, and this is the unbound electron. This is unbound electron which is responsible for the conduction. And we should know something here. After doping, the free electrons concentration is higher when compared with the hole concentration. So in case of N, the free electron concentration will be higher when compared with hole concentration. Remember this. For an N-type semiconductor material, free electron concentration will be higher when compared with the hole concentration. Free electron concentration will be higher when compared with the hole concentration. I can say N is greater than P. And you should remember here, the energy which is required to free this 5th electron will be very easy. Which will be given very, very less value. I think 0.05 electron volts is sufficient to detach this electron from this covalent the atom, because it's already free. It is already freely moving, and it requires very less amount of energy to detach itself from the complete atom. Okay. Now, here one more important thing to be remembered. This pentavalent impurities are called as donors. These pentavalent impurities are called donors. So why it is called donor? Just now I have told you. Donors. Just now I told you. What I told you, sir? What I told you, sir? So they are called donors. See, if we go back and see, in case of Na, I have clearly told you why this Na is called donor. So, and it represented with the positive atoms. So this Na has become Na plus by donating one electron. Na has become Na plus. And whereas in Cl accepted one electron and it has become Cl minus and it is called Cl minus. So here, so this arsenic is called as a donor. This arsenic is called as a donor, right? So which is very important. This is very important, sir. You should remember this. You should remember this point. Very important. So and I can call this as a donor concentration END also. I can call the donor concentration END. It is called END, the donor concentration ND. That is number of atoms per centimeter cube or per meter cube. How many number of atoms are added to a pure semiconductor to change it to an n-type semiconductor is nothing but a donor atom. It's called a donor atom. If you go back and see, so this is what I'm trying to mention here. A pentavalent impurity is added here. A pentavalent impurity is added here. So by adding a pentavalent impurity, you can see here a arsenic is added here. A free electron is generated, and we call it as an n-type semiconductor. N-type semiconductor. If you see, and it's a conduction band. Anyway, this energy band diagram we haven't discussed a lot. The donor level. Remember, the donor level will be always close to the conduction band. The donor level will be always close to the conduction band. This is very important. Okay, this is very important. So the donor level will be very close to the conduction band. You guys should remember this. You guys should remember this. Okay. The donor level will be close to the conduction band. Now we will see this now. Now this is the P type. This is going to be P type. In P type semiconductor material, now I have added a trivalent impurity of atom boron. Whenever boron is added, so boron has a trivalent. Trivalent means it has 3 electrons. It has 3 electrons in the outermost shell. It has 3 electrons in the outermost shell, out of which all the 3 are occupied. All the 3 are occupied by the covalent bonds, and you can see there exists one more free. The one covalent bond. In one covalent bond, there exists an absence of an electron, and that absence of electron is nothing but a hole. The absence of electron is nothing but a hole. Now what happens, sir? Now you can see a hole here. So after some time, what happens, sir? This electron may get some energy and it may jump into this. So moving now, what happens, sir? Whenever this electron is moving from here to here, it creates a hole here. Yes or no? It creates a hole here. So now this will be filled with electron. Next time, what happens, sir? This electron may jump here, and because of this hole will be moving in this direction. So this is electron moving, and this is hole moving. We discussed in detail what do you mean by electron movement and hole movement, right? So these are pentavalent atoms. These are called acceptors. Why these are called acceptors, sir? It is trying to accept one electron. I have told you that's also Cl minus also. So it is ready to accept one electron. So in this case, the concentration of holes will be very high when compared with electron. And this P is represented with something called acceptor. Acceptor concentration Na. This is represented with acceptor concentration Na. So remember this acceptor concentration Na. In case of P type, in case of N type, we call it as a donor concentration Nd, and in case of P type, we call it as acceptor concentration. Na. If you look at the energy band diagram, the acceptor level will be very close to valency band. Rather than being close to the conduction band. If you see in case of a n-type semiconductor, the energy level will be very close to the conduction band. But in case of a p-type semiconductor material, so it will be very close to acceptor. It is very close to acceptor level. And this is going to be valency band. This is going to be very close to valency band. In that previous case, it was very close to the conduction band. It was very close to the conduction band. Okay. So these are the points we should remember. This is the point we should remember very easily. Next. Next, here comes very important formula, sir. Many questions asked based on this formula. Many questions were asked based on this formula, something called mass action law. So what mass action law says is, I'll write the statement of this under thermal equilibrium. Under thermal equilibrium, the product of understand this, the product of negative and positive concentrations in a constant is a constant. The product of negative and positive concentrations, the negative and positive concentrations is a constant, which is independent of independent of the amount of acceptor impurities, donor and acceptor impurities. Remember this. So, this is very important. Under thermal equilibrium, the product of what is negative charge, sir? Negative concentration N and positive concentration means P, which is equal to, which is a constant. So, what is that constant? N into P is equal to Ni square. This is the most important formula which you guys should remember. So based on this, hundreds of questions can be asked in the examination many times. I think from last 20-25 years, definitely a question will be asked based on this formula. N into P is equal to Na square. N into P is equal to Na square. Right? N into P is equal to Na square. Very important formula. N into P is equal to Na square is very important formula. Right? So from this you should remember Na square, the intrinsic concentration is a function of temperature. Then where it depends, sir? On what bits it depends? So the intrinsic concentration, the Ni intrinsic concentration is a function of temperature. It means it depends on temperature. This Ni depends on the T. So how it depends, sir? How it depends? Just a sec. Oh yeah. So I'll try to do it. 1 second. Just 1 second. See, this Ni square is equal to A0 into T cube into e power minus Eg0 by Kt. Okay. So remember this Na square is equal to A0 into T cube into e power minus Eg0 by Kt. What is Eg0, sir? What is A0? First A0 is where A0 is equal to constant independent of temperature. This is a constant. So we'll derive this equation. Don't worry. You do not worry. We'll derive this equation. This is a constant independent of temperature. A constant which is independent of temperature. Then what is Eg naught? What is Eg naught, sir? Eg naught is going to be the energy gap at energy gap at 0 degrees Kelvin. Energy gap at 0 degrees Kelvin. And then what is KT? What is K? K is going to be Boltzmann's constants. Boltzmann's constant. Boltzmann's constant. Okay. So Na square is equal to T cube into e power minus Eg naught by KT. Eg naught by KT. A naught is A naught, Eg naught in K. Right? Okay. Next. The charge densities in a semiconductor. The charge densities in a semiconductor. According to law of electrical neutrality, now you should remember, according to law of electrical neutrality, according to the law of electrical neutrality, according to the law of electrical neutrality, for a semiconductor, the magnitude of very important, sir, the magnitude of positive, the magnitude of the positive charge, must be equal to positive charge density must be equal to positive charge density is equal to the magnitude of negative charge density. Negative charge density. Sir, in 2021, charge density. In 2021, a question is asked based on this simple charge of electrical neutrality. This was used in the 2021 GATE paper. You can go back and see my questions which I have discussed in detail. Okay, just go back and see. I have clearly in detail discussed about this question, GATE 2021. Right? Remember, the charge densities in a semiconductor is going to be. Now, what is the positive charge, sir? The positive charge is going to be. What is the positive charge, sir? The positive charge is going to be Nd plus P must be equal to Na plus En. You should remember this formula. This formula is very important. Nd plus P must be equal to Na plus En. It is not straight, no problem. So Nd plus P must be equal to Na plus N. Nd plus P must be equal to Na plus N, where Nd is a donor concentration. And Na is going to be the acceptor concentration. Donor concentration plus P, the positive charge. And Na, acceptor concentration plus N. Acceptor concentration plus free electron concentration N. So Nd plus P is equal to Na plus N. Nd plus P is equal to Na plus N. This is a very important, sir. I'm telling you, in 2021, a question was asked based on this concept. Right? So for an N-type semiconductor, you should remember now. So before going to conductivity, before going to conductivity, I should mention a very important thing here. I'll just go back. Very important thing I should tell you here. Very important thing based on this. Sir, I'll just try to discuss for extra. I'll take extra 5 minutes, extra 5 minutes. Hopefully, extra 5 to 10 minutes I'll take to finish up this topic, so that in the next class we'll discuss problems. We'll discuss problems, sir. We'll discuss problems directly in the next class. We'll discuss problem directly in the next class. That is why I'm just trying to push myself to another 10 minutes. Please bear with me for 10 minutes. Please bear with me for another 10 minutes. Please bear with me for another 10 minutes. Okay. For N-type, for N-type semiconductor material, so the acceptor concentration is how much, sir? For N-type semiconductor material, acceptor concentration is acceptor concentration is 0. Acceptor concentration is 0. Approximately equal to 0 actually. Approximately equal to 0. There is going to be Na is equal to 0. It means N is far greater than P. So from law of electrical neutrality we know that Nd plus P is equal to Na plus N. Na plus N. So this is going to be Nd plus P is equal to 0 plus N. So I can write, anyway this N is very high when compared with P. So what you can write, sir? N is approximately equal to Nd. Remember, N is approximately equal to Nd. If N is approximately equal to Nd, N is approximately equal to Nd, I can call this as a electron concentration in material, right? So now from mass action law, Nn into Pn must be equal to Ns square. Then from Pn, for that Pn is equal to be Ns square by Nd. Ns square by Nd. This is very important formula. Ns square by Nd. Pn is going to be. So these two are very important for a P-type. Okay. So for N-type. So for P-type semiconductor. For P-type semiconductor, what is the acceptor concentration, sir? What is the acceptor concentration? For P-type, what is the donor concentration? For a P-type, donor concentration is 0. Donor concentration is 0. For P-type, donor concentration is 0. That is Nd is equal to 0. If Nd is equal to 0, then P must be far greater than N. So again you consider Nd plus P is equal to Na plus N. Then this Nd is going to be 0 plus P is going to be Na plus N. Anyway, this N is very small when compared with P. So P is approximately equal to Na. P is approximately equal to Na. Very important. Right? That can I write this as a PP? PP into Np is equal to Na square. Pp into Np is equal to Na square. So from this, can I write Np is equal to Na square by Na. Na square by Na. This is a very important formula you guys should remember. These two formulas should be remembered very importantly for P-type and N-type. Okay, so these two are very important, sir. For N-type and P-type, Nn is equal to Nd, Pn is equal to Na square by Nd. For a P-type semiconductor material, Pp, the whole concentration in a P-type semiconductor material is going to be equal to the acceptor concentration. It's going to be equal to acceptor concentration. and NP. What is NP, sir? The whole the electron concentration in p-type semiconductor material will be equal to Na square by Na. Na square, sir. Based on this formula, many times many questions were asked. Based on simple formulas, based on this simple formula, many questions were asked in the previous examination. In the previous examination, many times the question was asked. Right? Many times the question was asked. Next. Next, here comes the conductivity. So, what is conductivity, sir? What is conductivity? We see, we have discussed from current density J, current density J is equal to, we have seen sigma into what, sir? E. Sigma E. We have discussed, yes or no? Where sigma is conductivity, and that was given as N Q mu, simply, actually. But for semiconductor, for n-type semiconductor, for n-type, so what is the mu, sir? Mu is going to be mu n, yes or no? Because the electron concentration will be very high. For n-type, so what are the majority charge carriers? For n-type, just now we discussed that electrons are the majority charge carriers. If the electrons are the majority charge carriers, the mobility of the electrons will be very existing, very high. Right? For p-type, this mu has to become mu p, right? So, for an intrinsic semiconductor, for an intrinsic semiconductor, both electrons and holes will exist or not? Both electrons and holes will exist or not? So, as both electrons and holes will exist, so we write this as sigma is equal to N Q mu n plus P Q mu p. Okay. NQ mu n plus PQ mu p. So for an intrinsic semiconductor, so conductivity sigma is going to be, you can take a Q out, then this will become N mu n plus P mu p into Q is what the conductivity is. Okay. This is what the conductivity. Sigma is equal to conductivity. This is for any type of for a given semiconductor. This is going to be for intrinsic semiconductor. N is equal to P is equal to Ni. N is equal to P is equal to Ni. If N is equal to P is equal to Ni, so what this formula becomes, sir? I can write this as sigma I is going to be Ni into mu n plus mu p into Q. This is very important formula. The conductivity for a intrinsic semiconductor is going to be this. The conductivity for intrinsic semiconductor is going to be this. Sigma I is going to be Ni into mu n into mu n plus mu p into Q. Why, sir? Because for intrinsic semiconductor, N is equal to P is equal to Ni. Okay. So, sir, we'll close it here because we're running short of time. So, we have something called plus subscription. Sir, so before this, let me just play one super video. This I just wanted to play from many days. Just watch this video, sir. Just a second. Just a second. Just give me a second.
Long years ago, we made a tryst with destiny, and now the time comes when we shall redeem our pledge. India will awake to life and freedom.
चल उठ जा, let's crack it, जोर दे लगा, let's crack it, खेड़ को छोड़ दे, let's crack it, रास्ते मोड़ दे, let's crack it, चल उठ जा, let's crack it, जोर दे लगा, let's crack it, खेड़ को छोड़ दे, let's crack it, रास्ते मोड़ दे, let's crack it.
साधारण सी है ये बात, परीक्षा करनी है पास, रोक के रखना अपनी सांस, अपनी एक ही आस पीछे सारे मंत्र और रट ले सारे फॉर्मूले, जब तक पार लगे ना नहीं है तब तक रेस्ट ना तू ले। तो इस बार तू आड़ दे, 6 फुट अंदर गाड़ दे, आसमां को फाड़ दे, जोर से दहाड़ दे, अंदर की आवाज सुन जो तेरे भीतर आई है। जोर लगा तो जोर लगा,
let's crack it,
लड़ जरा कुछ कर दिखा,
let's crack it,
लड़ जरा कुछ कर दिखा,
let's crack it.
जोर लगा तो जोर लगा, लड़ जरा कुछ कर दिखा। दुकानें है बड़ी, इनकी भोगते बड़ा भारी है, बिका है पकवान इनका, शिक्षा के व्यापारी है। एक नंबर तेरा काम, फीस यहाँ बहुत ज्यादा है, तू बाकियों से पीछे है, तू देख तो कितना नीचे है। उसके बाप का सिक्का चलता है, तेरा बाप कमाता सिक्के है। मत सुन इनकी ये धुन इनकी, तू बढ़ता जा बस लड़ता जा, क्रैक करते जा, क्रैक करते जा। जोर लगा तो जोर लगा, लड़ जरा कुछ कर दिखा।
Let's crack it, जोर दे लगा, let's crack it, खेड़ को छोड़ दे, let's crack it, रास्ते मोड़ दे, let's crack it, चल उठ जा, let's crack it, जोर दे लगा, let's crack it, खेड़ को छोड़ दे, let's crack it, रास्ते मोड़ दे, let's crack it.
बेटा सिस्टम का ये जोड़, तेरे हाथ पे ये सब गोल, तू है भटका हुआ भूगोल,
Let's crack it,
देगी तुझको बस ये दुनिया, खूब निराशा खूब हताशा,
When we shall redeem
खूब निराशा खूब हताशा। मत सुन इनकी ये धुन इनकी, तू बढ़ता जा बस लड़ता जा, क्रैक करते जा, क्रैक करते जा। जोर लगा तो जोर लगा,
let's crack it,
कुछ कर जरा कुछ कर दिखा। जोर लगा तो जोर लगा, किस्मत तेरी मेहनत बन के मौका बेटा लाई है, क्रैक करते जा, क्रैक करते जा। चैलेंजेस उठाए जिससे ट्रॉफी भी उठाई है, क्रैक करते जा, क्रैक करते जा। अंदर की आवाज सुन जो तेरे भीतर आई है, क्रैक करते जा, क्रैक करते जाना, क्रैक क्रैक करते जाना, क्रैक क्रैक करते जाना, क्रैक क्रैक करते जाना, क्रैक।
let's crack it, चल उठ जा, let's crack it, जोर दे लगा, let's crack it, खेड़ को छोड़ दे, let's crack it, रास्ते मोड़ दे, let's crack it, चल उठ जा,
कर दिखा कुछ, क्योंकि तेरे हाथ में है करने का अभी मौका, तेरे पास में है, करते जा, लड़ते जा, हिम्मत नहीं हार, सबको करके दिखा। क्या
let's crack it, जोर
तेरा भाई तेरा दोस्त इससे बोल रहा, कर दिखा, लड़के दिखा।
रास्ते मोड़ दे, let's crack it.
So let's crack it, sir. Let's crack it. Get inspiration from this video. So be always strong. Be always strong. Get inspiration from this video, right? So I wish you all the best for all of you. So this is going to be a plus subscription we have. We have a plus subscription which will give you access to live classes. You can attend all the crash courses. You can write the weekly test. You can write all the weekly tests, and you will be having a doubt solving session. So every 4th hour is going to be a doubt solving session. The sessions will be English and Hindi. You can attend those students who don't understand English, they can attend in Hindi. And we have something called rank improvement batch. And we have icon subscription. Along with the benefits of the plus subscription, we have something called a personal coach. You'll be given a study planner. You'll be given a study booster sessions. You'll be given a personal test analysis. A preparatory study material will be supplied to you. The the plus subscription for 12 months is going to be 27,225 rupees. Plus subscription for 18 months is going to be 34,650 rupees. Plus subscription for 24 months is going to be 39,600 rupees after applying the code SVS10. And iconic subscription for 12 months is going to be 45,225 rupees. Iconic subscription for 24 months is going to be 66,600 rupees. That is SVS10 code. You should use the code SVS10 to get 10% discount on it. Okay. All my class notes will be available on Unacademy GATE English channel. Please download them. So, and as I told you, I'm teaching on Unacademy GATE English. So we have extra Creatrix GATE ECE, EEE and instrumentation. Unacademy GATE for mechanical production engineering and engineering sciences, we have separate channel. Unacademy civil engineering and chemical engineering, we have. Unacademy computer science and information technology, we have. Unacademy GATE questions, we have separate channel, and we have separate channel for electrical engineering. A separate channel for electrical engineering, right? So thank you, and please don't forget to like the class, share the class, subscribe the channel, hit the bell icon, right? Thank you. I wish you all the best. We'll catch up next time, right? Thank you. All the best. Bye.